Hi guys, so today we're going to be doing geometric probability and area of sectors. Before we get started with our first example, let's talk about what geometric probability is. Okay? So probability that involves a geometric measure such as length or area is known as geometric probability. Okay? In a previous chapter you learned that the probability that a point lies on a part of an arc can be found by comparing the length of the part to the length of the whole arc, right? So we saw that with a circle, right? So like the circle, right, the whole length we know is the circumference, and then given a certain angle measure, that in comparison to the whole 360 of a circle can help us find what fraction of the arc we want. Okay? So that's how that comes into play. Okay. So probability and area. So if a point in region A is chosen at random, then the probability of choosing something from this circle here, this B area, is the area of region B over the area of region A, right? So still what we want, the idea of success over failure here, okay? So here, a square game board has black and white stripes of equal width as shown. We want to know what is the chance that a dart that strikes the board will land on a white stripe. And then in this picture, it's a little bit hard to see here, okay? But really what happens is each of these are 6 units. So each one here is 1 unit. Right, so this is 6. And this here is 6. So the total game board is 36 small unit squares. Okay? And then if we were to count, or you can actually just find the area if you wanted to, but here since it's easy we can just count them, right? Or we could do 1 times however many, 1, 2, 3, 4, etc. Okay? So here the total is 6 times 6 of them. There's 36 squares here. And then how many of the small squares there are? There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then 15. So 15 over 36, which you can simplify. Both are divisible by 3, 5 over 12. All right. So probability, you could write it as a fraction. Okay. You could also write it as a decimal. Okay. Or you can write it as a percentage, 41.6 bar repeating percent. Okay. So both of these, all 3 of these are acceptable, right? But the 5 out of 12 is probably might be easier to visualize. It's nice and easy compared to the repeating decimal here. Okay, so why don't you try CYP1, find the probability that a point chosen at random from the figure lies in the shaded region. Okay, you should have gotten half, or 0.5, or 50%. If you got that right, you can move on to the next example. If not, here is your explanation. Okay, there's a total of 64 squares in here. It's 8 this way and 8 this way, for a total of 8 times 8, 64. Okay. And then for the shaded one, I just counted them, 1, 2, 3, 4, 5, and then counted there's 32. Okay. The other way you would do it is you would do 1 times 1, 2, 3, 4, 5, 6, plus 1 times 1, 2, 3, 4, 5, 6, plus 1 times 1, 2, 3. Like that's another way you could do it too. Right. But because this is nice and it has squares all marked off, right, nothing's divided or anything or split into weird shapes, it's just easier to count here. Okay, our next example is going to deal with probability with sectors. Okay, so it's important that we know how to find the area of a sector. Okay. So sometimes you need to know the area of a sector of a circle in order to find the geometric probability. Okay? A sector of a circle is a region of a circle bounded by the central angle, right? So we know the central angle, the vertex is at the center, okay? And its intercepted arc. So this is a sector, right? Because central angle, here's the arc, this is the sector. Okay? And then similar to finding arc length, right, where we did circumference and then whatever this is over 360 times the circumference, right, we're doing the same thing here, right, because we can, using proportional reasoning, we can derive the formula for the area of a sector, right? So n degrees, however much this central angle is out of the total 360, gives us what portion, what fraction of the circle or the area that we want, okay? And then we can just multiply that by the area of the circle, which is pi r squared. And so the area of the sector is the area of that angle, that central angle, sorry. The area of the sector is the measure of the central angle over 360 multiplied by the area of the circle. There we go. Okay, so let's take a look at example 2. We want to find the area of the blue sector. Okay, so the blue sector is 46 degrees. That the central angle is 46 degrees. So out of the total 360, okay, because all of these degrees add up to 360, we want only 46 out of the 360 of them. Okay, out of the whole area. The whole area is pi r squared. Okay. Here the diameter is 12, so radius would be 6. Okay. So then let's find that area. So 46 divided by 360. 6 squared is 36, so times 36. And then times pi. This gives me 23 over 5 times pi. 23 over 5 is 4.6, so that's why you see your book write it as 4.6 pi. Okay, these are the same thing. So that's the area of the sector. Okay? Find the probability that a point chosen at random lies in this region. Okay? So that means it's that 4.6 pi, what we want, over the whole area, which we know is 36 pi. Right? Because pi r squared, radius is 6. Right? So that's the whole area. Okay? The pi and the pi cancel out, so really it's just 4.6 divided by 36. Okay? And then that is approximately, it is 0.12 bar repeating for the 7, or 12.7 bar repeating percent, or your book approximated that to about 13%. Okay? So written as a decimal, written as a fraction, and then this is the rounded answer. I should put it in 0.13. Okay. So why don't you try CYP 2A and 2B, and then once you're done, come check the answer. Okay, for 2A you should have gotten 8 pi. For 2B you should have gotten 2/9, or as a decimal it's 0.2 with a bar repeating, or 22.2 with a bar repeating percent. Okay? If you got that right, you can move on to our last example. If not, here is your explanation. Okay, so orange sector is, this is 80 degrees, so 80 out of the 360, that'll give us the fraction of how much of the circle we want. Okay, and then the area of the whole circle is pi r squared, pi 6 squared, okay, and that simplifies to 8 pi. Okay. And then for 2b, find the probability that a point chosen at random lies in this orange region. So 8 pi is the area of what we want over the whole area, which is pi 6 squared, which is 36 pi. Okay, the pi and pi cancel out. 8 over 36 simplifies to 2/9. Okay, and then this is it as a decimal, and this is it as a fraction. Okay, then example 3 talks about segments. Okay, so before we get to example 3, let's look at the book in regards to segments. Okay, so the region of a circle bounded by the arc and the chord is a segment, right? So sector is central angle and arc. Segment is chord and arc. Okay? To find the area of a segment, you just need to subtract the area of this triangle formed by the radii and the chord. Okay? There you go. Okay. So example 3. So a regular hexagon, a little blurry, hold on. A regular hexagon is inscribed in a circle with a diameter of 14, right? So here's the circle, here's the hexagon. Note that the diameter is 14, okay? We want to find the area of the red segment, okay? So if the diameter is 14, the radius is going to be 7. Okay? So several things come in here at play. So we want the area of the whole sector. So we're going to do area of the sector. Okay, so that's this whole piece here. And then we're going to subtract the area of the triangle, and that will give us the area of the segment. Okay, so area of the sector, right? So here, this is a hexagon, so 360 all the way around, divided into 6 pieces. So that's 60 out of the 360. Okay. Then pi. If diameter is 14, that means radius is 7, so 7 squared. Okay. Then we're going to subtract the area of the triangle. Okay, so here you see a close-up of the triangle, right? So these are formed by the 2 radii, so this is 7 and this is 7. Okay, we know that this is 60 degrees, and so when we split it here to get the height, this creates a 30, 60, 90 triangle. And so since this is the hypotenuse, this here is 3.5. Okay. And then this long leg is 3.5 times square root of 3. Okay, so that's the height. Right? So 30, 60, 90 triangle, it's all coming back. This is 3.5 times square root of 3, which your book approximated. Okay? So then the area of this triangle that we're going to take out, right? Because right now area of sector is all of this. We want to take out the triangle. So area of the triangle is 1/2. The base here is 7. Okay, we just found that here because it's an equilateral triangle. Base is 7. And then the height, which I found here, right, is 3.5 square root of 3. Okay. 60 divided by 360 times 49. This becomes 49 pi over 6, and I'm going to subtract 7 times 3.5 divided by 2. This becomes 12.25 square root of 3. Okay, and now I'm going to simplify everything. So 49 pi over 6. 6 minus 12.25 square root of 3, and that gives me approximately 4.4. I'm going to write it more. 4387 units squared. Okay. So to find the probability that a point chosen at random lies in that red region, then it's going to be the area of that red region, which is 4.4387, over the area of the whole thing, which is pi r squared. Pi radius is 7 squared. So we want this, 4.4837 over my 49 pi, right, divided by 49 pi. Right, and then that gives me approximately 0.02, hard to see on my calculator, 0.0288, or approximately 3%, or 0.03. Okay, those are all close approximations. Okay, so why don't you try CYP 3A and 3B, and then once you're done, come check your answer. Okay, you should have gotten about 22.1 for 3A, and then for 3B, you should have gotten about 0.20 or 20%. If you got that right, you can get started on your homework. If not, here is your explanation. Okay, so area of the shaded region, this is a segment. So I'm going to do area of the sector minus area of that triangle. Okay, so here, since this is an equilateral triangle, right, it's going to be 360 divided by 3, so that's 120 degrees. So then this central angle here is 120 degrees over the 360 times the whole area of the circle, pi r squared, or pi 6 squared. Okay? Then subtracting the triangle. So here I did a zoom in of the triangle, right? So here, if each of these central angles is 120 degrees, and then it's equilateral, so this is 60. When I split it here to get the height, this half of 120 is 60, and then this 60 degrees here gets split in half, which is 30. So it becomes a 60, 30, 90 triangle. Okay. The diameter is 12, which means the radius is 6. So that's why here is 6, right? And here is 6. Okay. So since that is the hypotenuse, that means short leg is 3, which means long leg is 3 square root of 3, or this whole thing doubled that is 6 square root of 3. So then triangle here is 1/2. The base is 6 square root of 3. And the height here is 3. Okay. Then I just simplified this. This becomes 12 pi. This becomes 9 square root of 3, which is approximately this. And then the book just rounded it to 1 decimal place. Okay. Then doing the probability of that, this is what we want. This is the desired outcome over the total possibility. On that circle, it's an area of 36 pi, right? Pi r squared, radius is 6. Okay, and then simplifies that, and I get approximately 0.1955, which the book approximated to 0.20 or 20%. Okay. That's it for today. Have a great rest of the day. Bye, guys.